We present our work on independent subspace analysis for unsupervised learning of disentangled representations. This is joint work of Jan Stuehmer, Richard Turner, and Sebastian Nowizin from Microsoft Research Cambridge and the University of Cambridge. Representation learning aims to reconstruct underlying generative factors of observed data. A commonly used dataset for evaluating such approaches is the G-sprites dataset, which consists of images of sprites of different shape that change their scale, rotation, and position in the image. As such, the generative factors of the dataset are the sprite's shape, scale, rotation, and x and y positions. The aim of representation learning is to reconstruct these generative factors just by observing samples from the dataset. Furthermore, often models are sought that disentangle these generative factors. A common understanding for disentanglement is that each latent variable is associated with a distinct generative factor and that the latent components are independent from each other. We built upon existing work that utilizes the Variational Autoencoder framework for representation learning. A Variational Autoencoder is a latent variable model that combines a generative model, the decoder P, a deep learning model with parameters theta, with an inference network, the encoder Q, with variational parameters phi. Training is performed by optimizing the evidence lower bound, the so-called elbow, averaged over the empirical distribution. The elbow consists of two parts: the reconstruction loss of reconstructing the data X given the latent Z, and the Kaibeck-Leibler divergence between the approximate posterior of the latent distribution given the input data and the latent prior. The approximate posterior is usually modeled as a multivariate Gaussian distribution, and for the latent prior, most approaches use the normal distribution. Higgins et al. Proposed in their work beta-VAE to modify the elbow objective by introducing a weight for the Kaibeck-Leibler divergence. A value of beta larger than 1 means that we are less confident about the data and results in a stronger influence of the prior. Kim and me propose factor VAE that penalizes the total correlation between the dimensions of the latent representation. They optimize this term with a density ratio check. Chen et al. Present TCVAE, where they use a tractable Monte Carlo estimate for this term. In this experiment, we demonstrate that using a higher weight for the KL term amplifies existing biases of variational inference, namely orthogonalization and pruning. To demonstrate this, we use mean-fit variational inference and apply to factor analysis. We use a sparse student C distribution and generate data from 3 latent components in a 2-dimensional observed space. The directions of the 3 weights are shown in blue with data as blue circles in the left plot. First, we run standard variational inference with beta equals 1, finding the components shown in red, which are more orthogonal than the true directions, as you can see in the plot in the middle. This bias is in this directions, as this reduces the dependencies in the underlying posterior. Second, we run beta variational inference with beta equals 5, which result you can see in the plot on the right. 2 components are now found that are orthogonal with 1 component pruned from the solution. In this case, the bias is so great that the true component directions are not discovered. Instead, the components are forced into the orthogonal setting regardless of the structure in the data. This is disentangled, but would lead to incorrect interpretation of the data. Arguably, beta-VAE is enhancing a statistical bug in variational inference and leveraging this as a feature. We believe that this can be dangerous, preventing the discovery of the underlying model. Instead of modifying the objective function, we propose to use a beta prior to learn a disentangled representation. There's another drawback of existing methods for representation learning using VAEs. VAEs typically use a Gaussian prior for the latent variable. When our goal is an interpretable latent space, this is in general not a good prior because of its rotational symmetry, which results in non-identifiability of the latent representation towards the rotations of the latent space. This is well known for other latent variable approaches, for example for probabilistic PCA. If we wish to remove the degeneracy associated with latent space rotations, we must consider non-Gaussian latent variable distributions, giving rise to independent component analysis models. A generalized version of ICAI uses a prior from the family of exponential power distributions of the following form. We can reparameterize the exponent to obtain a parameter beta as a measure of kurtosis. This family of distributions generalizes the normal and the Laplacian distribution. For beta equals 0, we obtain the normal distribution. For beta equals 1, we get the Laplacian distribution. In general, we get for beta larger than 0 leptokurtic and for beta smaller 0 platykurtic distributions. Examples for the different shapes of distributions are depicted on the right. ICA can be generalized to model independency of individual subspaces by using a more general prior, the LP-nested symmetric distributions, as proposed by Sintz et al. Instead of the LP norm in the exponent, we choose functions of the following form, which we will call LP-nested. In this example, we have two nested LP norms, which structure is visualized as a tree above. For the components Z2 and Z3, we take the P1 norm. The result of this norm then contributes to the P0 norm together with Z1. Here we visualize the different shapes of isosurfaces that can be obtained with LP-nested functions. By taking a value of 1 for both exponents, we obtain the shape of a multidimensional Laplace distribution, as depicted in the top left. Taking a value of 2 for both exponents results in the Gaussian distribution, as you can see in the middle. For large exponents, the shape converges towards the uniform distribution. We can also combine different exponents for different dimensions. For example, we can model a Gaussian dependency between two dimensions by taking an exponent of P1 equals 2 and a Laplace distribution towards the remaining component by setting the exponent P0 equals 1. The resulting shape is depicted in the first row in the middle. ICA can be further generalized to independent subspace analysis by using LP-nested functions of this form. In this example, P0 denotes the exponent of the outer norm over all of the subspaces, and exponents P1 to P4 are the exponents of the subspaces. Using individual exponents for each subspace results in independency of these subspaces. Therefore, we can build a hierarchy of independent subspaces in latent space. We can use the LP-nested functions to define a probability distribution by normalizing a radial distribution over the surface area of the LP-nested sphere. This surface area can be computed by using the gamma function. The radial distribution can be interpreted as a generalization of the chi distribution. We performed our quantitative evaluation on three datasets: the Dispuites dataset, 3D faces with the generated vectors horizontal and vertical viewing direction and light direction, and cast 3D with the generated vectors shape and color and vertical and horizontal viewing direction. We performed an extensive quantitative evaluation and trained a total number of 2,240 models for evaluation in our experiments. We measure the amount of disentanglement of a model by computing the mutual information gap, the so-called MIG score. To compute this metric, first the mutual information between every latent variable and the underlying generated vectors of the dataset are evaluated. The mutual information gap is then defined as the difference of the mutual information between the latent variables with highest and second highest correlation with an underlying vector. In this plot, the MIG score is plotted along the vertical axis, and a higher score means a better disentanglement of the representation. Along the horizontal axis, we plot the reconstruction quality of the model, where the reconstruction quality of a model increases from left to right. Because the modified ELB objective of beta-VAE and TC-VAE lead to a trade-off between disentanglement and reconstruction quality, a lower beta value usually leads to a better reconstruction quality. Here we present results on the Dispuites dataset. For the ICAI model, we define 5 subspaces with 4 components each, and manually set the outer exponent P0 to 2.1 and the exponent of each subspace to 2.2. We perform an extensive evaluation. For each approach, we train 50 models per parameter setting, which results in a total of 1,600 experiments that are aggregated in this plot. The plot depicts the mean and the standard error for the 50 experiments of each parameter setting. The proposed approach ICAI allows a better trade-off between disentanglement and reconstruction quality, often outperforming beta-VAE and beta-TC-VAE with respect to MIG score and reconstruction loss, while beta-VAE and beta-TC-VAE reach better MIG scores only for models with poor reconstruction quality and for high settings of beta. Instead of manually tuning the exponents of the ISA model, they can also be learned during training. This plot depicts the results for training on the 3D faces dataset with 15 experiments per parameter setting. Thus, the plot aggregates the data of 360 experiments. We learn the exponents of each subspace and keep the outer exponent P0 fixed at 2.1. We initialized the exponents of each subspace to 2.0 and optimized them during training of the whole model. Interestingly, optimizing the exponents during training enables even further improvement of the trade-off between disentanglement and reconstruction quality, significantly outperforming the baselines for small beta values. In fact, strongest disentanglement is achieved with ICAI and beta equals 1 without the need to modify the alpha objective. This demonstrates that the prior greatly enhances disentanglement of the latent representation and significantly mitigates the trade-off between disentanglement and reconstruction loss. We also evaluated the proposed approach on the Cas3D dataset and performed 35 experiments per parameter setting. Thus, this plot aggregates the results of 280 experiments. For small values of beta, and especially for beta equals 1, ICAI outperforms beta-VAE and leads to better disentanglement with comparable reconstruction quality. This brings us to our conclusion. We demonstrated that increasing the weight of the KL term increases the over-pruning bias in variational inference. To mitigate the drawbacks of existing representation learning approaches that are based on the beta-VAE framework, we propose to use a prior from the family of LP-nested symmetric distributions that defines a hierarchy of independent subspaces in latent space. In contrast to the frequently used normal distribution, this prior is not rotationally invariant. The prior results in a significant improvement of the trade-off between disentanglement and reconstruction loss, and we demonstrated that this trade-off can be further improved by learning the exponents of individual subspaces during training. This concludes my talk. Thank you for listening.